Okay, now what about the final velocity just before it hits the ground? Well, we get acceleration from 0. We could just do acceleration multiplied by the time. Done. But at least for now, you are generally expected to actually write down your formulas. Plus g delta t, which is equal to 0 plus negative 9.8 times time. Now, when you round, you should not use that for your next step, usually. In some areas, it's okay, but usually you're supposed to keep at least a few more digits when you round, or better yet, just keep the fractions outright. Whether you write VF here again, well, usually it's fine if you just write it for the first and then the last one of when it stays the same. In this case, that's times 9.8 negative. So that's equal to negative 140. And this is in meters per second. Wait a second, this is a vector and we have a negative speed. Negative speeds are not a good idea, because speed is just a size. It doesn't care which direction you're going. So negative would have to be this. So the final velocity is 140 meters per second down. Notice the change to give a positive number, because positive numbers are often more practical to use in everyday life. All right, so let's say this time we're going to shoot a cannonball directly upward. There are many reasons why this is not considered the most intellectually brilliant of ideas, especially in an environment where free fall is considered valid. I don't think I need to explain why, right? Okay. So determine the time for the cannonball to reach its maximum height. What happens at its maximum height? Well, it stops moving up and then comes moving back down again. Okay, that means we need to bleed away all this initial upward speed, which in this case comes out to, if we want to write the whole formula out, we get this: VF equals VI plus G delta H. So we know that the final velocity was 0 because it goes up and then it stops at its maximum height. And this is equal to 800 meters per second upward, which is positive 800 because we treat up as positive, plus negative 9.8 times delta t. We keep everything where it is for the substitution step, and then we start moving things, such as move this whole thing over here, so that becomes positive 9.8 delta t, and then just divide the 9.8, and this gives us 800 over 9.8, which is approximately, because telling somebody that it takes 800 over 9.8 seconds is not a very useful number. So 800 divided by 9.8 is approximately, well, there are 3 significant digits because 800 was the number we were given, 81.6 seconds. The ball reaches max height at approx 81.6 seconds. Now find the total time the cannonball takes from launch to return to the launch point. Our position time graph is gonna be a parabola. It is symmetrical. It goes up and then it comes back down in exactly the same way except in reverse. So like that. Because there's no air resistance to take energy away to slow the ball down, it will arrive back at its launch point at exactly the speed it was launched at. Yeah, we could say that. What else could we try? Well, we know that given delta H is equal to 0, gravity equals negative 9.8, and you could state in units. But make sure that you get your directions correct if you put signs that are not positive, so negative. And what else do we know? We know that the initial velocity VI equals 800 meters per second up. Well, we want the time, so want delta t. In this case, we've got to deal with delta H is equal to VI times delta t and plus 1/2 g delta t squared, which means 0 is equal to 800 delta t plus 1/2 negative 9.8 times delta t squared. Now, one solution to this is that time is 0. 0 equals 0 plus 0. But that's not what we're looking for. We're looking for the other one. That means we can cross this and this out. We can just divide by delta t. And what happens? Oh, we end up with 800 over here and 4.9 delta t on this side because we multiply and then we move that. So delta t is equal to 800 over 4.9. Which is approximately 163. Wait a second, guys. We have 3 significant digits to work with, 800. So that's just 163 seconds. Yes, different numbers of decimal places might seem kind of awkward, but, well, this is a significant digit convention. The ball returns after approx 163 seconds, twice the time to max out. Time to max, well, height is enough. Also known as altitude. Now find the maximum height the cannonball could reach from the point it was launched. Hey guys, it took 800 over 9.8 for time. So Vf equals 0. Vi equals 800 meters per second up. Delta T is equal to 800 over 9.8. And therefore, well, we have delta D equals Vf, that's a vector 2, plus Vi over 2, so the average velocity, multiplied by the amount of time it took. Which means we end up with 0 plus 800 over 2 multiplied by 800 over 9.8. And that is, well, we could just change this to 400. 400 squared divided by 4.9, because we could change this to 400, and then this is 400 over 4.9, and that's approximately 32,653 meters up. Now there's a bit of an issue here. We have 3 significant digits to work with, 800 for the 800 meters per second. So here we can only keep 3 by the significant digit convention, which comes out to 3.27 times 10 to the 4th meters up. And, well, the statement is the max height is approx 3.27 times 10 to the 4th meters up. All right. In summary, we use the symbol g to represent the acceleration due to gravity. Now, yes, if we're representing a gravity as a force and so on, we give it a direction. That direction is downward. And in the case where we're using gravity as a vector, as opposed to just a representation, because after all, when you say force due to gravity, you do not put Fg. No, you put just Fg, usually. Which means this symbol is used to represent gravity. If we're talking about the acceleration due to gravity, we use g with the vector symbol. Now, all objects in free fall close to Earth's surface will accelerate at 9.8 meters per second squared toward Earth's center. If you don't add on the direction, if you don't tack on the direction, you can say that g, without the symbol, equals 9.8 meters per second squared. Some areas don't require you to put the symbol on g at all, as long as you make it clear that you're actually talking about gravity instead of a variable a, b, c, d, e, f, g. Now, air resistance can cause objects to accelerate at values less than g, and in fact, acceleration eventually stops during actual falling scenarios because of the air resistance getting so big due to the object's speed or perhaps its orientation, like spreading one's limbs as a skydiver and increasing the surface area as a result. Well, the object's air resistance due to speed or other changes, like say opening the parachute, eventually gets so much that the acceleration becomes 0. the force of air resistance completely balances out the force due to gravity. And indeed, when you first open your parachute, you usually feel a sudden jerk and then acceleration back up because you're slowing down. The force of air resistance has overcome the force of gravity. Now, when an object reaches terminal velocity, it falls at a constant velocity, so zero acceleration, until something changes. For example, the air resistance gets bigger due to opening a parachute. Or, well, the air resistance perhaps gets smaller due to changes in orientation. Well, that's it for this section. And next section, we get to notice the not minor fact that the world does not work in one dimension at a time. When you're throwing a basketball toward the net, the hoop, you are not just throwing it straight up, hopefully. If you want to score points, you kind of also need to make sure that it moves sideways. So that's 2 dimensions. And well, the world that we're used to handling and will be handling for most of kinematics is 3-dimensional in reality. For grade 11 kinematics, though, it tends to be 2 dimensions, which is what we'll get started on next section. So, see you later.